So these are the things that I've kind of got prepared. Like I said, I made this presentation for some colleagues at work.
Okay.
I'll talk about why I started, how I got down this long-ass rabbit trail, and then we're going to look at what heliocentrism is, and because that's where the majority of my effort and research was spent, because so much of what we're taught in school depends on assumptions from that. So I was really trying to understand all the assumptions that we were working with since basically since childhood. And then you were asking me about my own research and my own use of the scientific method. And that would be my quest for empirical proof. And then I've got a section just verifying my own math where I've done things on AutoCAD and I've drawn it up and I've tested my predictions. And then I've got some experiments that I haven't done yet that I still want to do.
Okay.
So I'm calling this presentation My Sincere Study of Geodesy, and that's not exactly words that are commonplace. Geodesy is determined as the study of the shape of the earth. And so that's basically what I'm doing. Like, I'm not out here trying to prove that the earth is flat. I'm not out here trying to prove that it's a globe. I'm literally just trying to research and learn more about what the truth of it is. The term flat earther has been pretty negatively stigmatized in the past 30 years or so. And I can't even totally claim to understand the full nature of our world. I don't have a full and complete model. I'm really studying what I have and what the shape of this earth is. And the answer to why comes actually from a student that I had in 2019 who asked me if the world was flat. It's a pretty normal debate question, and it comes up quite a lot in school, but I've never had a student ask it to me seriously. I've just had students ask me how they could win after they've lost. So that was pretty weird to me, and I told her the earth wasn't flat, but I really didn't have any reason to prove it to her because I was far more used to training students to win the flat earth debate. Not that I ever thought it was real. It's an exercise. To be able to get the kids to stop appealing to authority, but you go outside and just look and go, oh, I see flatness. Like that takes some time. So she asked me this after class in a rather serious way because she was watching something on YouTube. I just told her it wasn't, but I asked her for a week, and then I told her I would have a nice rebuttal and a perfectly little done paper, and she'd understand the world's not flat and it'd be over. And that never happened. I never got back to her, but like I guess a year and a half later, about a month ago, I sent her a link to one of my very first flat earth debates, and she just died laughing. She's forgotten about it and moved on, and here I am still tortured trying to answer the question. So what makes my study sincere? How am I different than everyone else in the world who's doing this? And the main thing is that at the very beginning, I refused to rest on assumptions. All hypotheses needed to be verified. I only cared about predictable phenomena. And now it wasn't necessarily a phenomena that I've seen. There's a lot of things, especially with the motions of the stars, since I live in a city of 15 million people, I haven't actually seen. But they're experiments that have been reproduced for thousands of years, and they're ones that I'm confident that I'll be able to reproduce once I'm no longer living in the city. And I've got a lot of literature to make me believe that. There are other experiments that I'll talk about in here, like some of Einstein's, where I doubt their reproducibility. And the literature doesn't exactly tell you how to reproduce it, and that's my problem. So predictable observed phenomena became my only laws, but not necessarily the phenomena that I had seen, or else I couldn't talk about eclipses at all. I've never seen a single, oh no, I saw a lunar eclipse once. I've never seen a solar eclipse in my life. I was in Vietnam during the Great American Eclipse.
Have some coffee.
It's early.
Yeah.
So I went to study exactly what scientific law is to try to bring clarity to my thinking. I wasn't really a scientist before I began this. I was much more of a philosopher. I was teaching political sciences and debates. And so everything was a theory to me. So to be able to entertain that the world was flat wasn't that hard because I taught debate and philosophy. I should be able to entertain everything. So I started to study the difference in science. What's the difference between a law and a theory? And it took me a second to understand because there's more steps to it than that, especially when you start talking about math. Like there are mathematical constants, and we call those things mathematical laws, but they're very different than a scientific law. And this is what we were touching on yesterday when you asked me if I believe or if I would jump off the cliff because I don't believe in the common knowledge. I don't believe in gravity. And in reality, I don't believe in what they call gravity. I don't believe in Einsteinian gravity at all, but that's the explanation of why this phenomenon occurs versus the description. I do know the phenomenon occurs. I know everything drops, and that's why I won't jump off the cliff. Why I'll drop is not a concern to me. I just know that I will. And so somewhere in between this law and theory, we have what we can trust. And there are some people who would argue with me, and they would say the middle is the theory and the left is hypothesis, but it's not totally accurate because science never says it's decided. Science never claims to be the final answer. It's a very opposite of its understanding and its methods. Everything should be able to be built on and changed if more evidence comes to light, if you discover more phenomena. So these are the phenomena, these are the laws that we're going to talk about mostly in this. The sun does set, and it's predictable based on the previous year. Sun rises every day in Vietnam, every single day in this country. The sun will rise. The seasons do change, not so much where I'm living now, but I remember back in Maryland where we'd have snowstorms and we'd have summer. That's obviously true. And the sun looks to be in a different place when that happens. Solar and lunar eclipses, and this is a big one, are predictable based on an 18-year, 11-day, and 8-hour cycle. So we've been taught that we figured out eclipses, but in reality, just like the sun, where if I wait a year and it'll rise at the exact same time, anytime I see an eclipse, if I wait 18 years, 11 days, and 8 hours, I'll see that exact same eclipse again. We know that on August 21st in 2017, there was what we call the Great American Eclipse, where it started in Washington, went all the way down to Florida, and almost all of America saw a total solar eclipse. If we looked at our calendar and we just minus 18 years, so sometime in 1999, that pattern should have been just about exactly the same, and sometime in 2036, we should see it again. The fixed stars are, in my terminology, just what you call stars, as opposed to the wandering stars, which are what you've been calling planets most of your life. The fixed stars, they do a complete circle. It's not really 24 hours. It's actually 23 hours and 56 minutes, while our sun does a 24-hour circle. Because unlike the sun, the stars don't change with the seasons. Now, since they're not going the same speed, what stars will be visible during our nighttime from a specific point of view of Earth will change with the seasons because the stars and the sun don't go at the exact same speed. If we were rotating on our own axis, I do wonder why they wouldn't go at the exact same speed, though. I would think they should.
So just so I understand, you're saying that the sun revolves around the Earth.
I would say above, but yes.
You say what?
I would say above instead of around. Let me give you a representation real quick.
Okay.
Gotta launch an application.
Okay. What is this I'm seeing behind you?
That's just a random animation with my green screen.
Oh, cool.
That's a Zoom feature.
You got a green screen and everything, huh?
Well, that's actually was for something I was doing with Dad. We recorded a tech video where I needed to do a walkthrough, and I didn't want my room as a background, so I went and bought one. And then I was teaching online for a while because I'm a teacher out here, and I was using it That's why I have the virtual background ready, because my students loved it.
Right.
All right. So this is my conception, as best as I have it, of the Earth.
Okay.
So right now, if you look at the top left, you can see the time. I'm gonna speed the time up a bit so we can watch how the sun would go.
Where's the sun?
See it on the hour hand? Yep.
Yeah.
So we'll see.
Oh, so you're saying the sun spins around the Earth, but not
doesn't go under it. I don't like. There's always day somewhere on the Earth.
Right. But so, do you have a slide that'll show me where how the sun does this around a flat disk? If you're saying the Earth is flat, right? So the sun, where is the sun in relation? So the sun shines at the Earth at a.
I think it's about 3,000 miles up, but I'm stealing ancient Greek smack when I say that. It's not my own.
3,000 miles?
Yeah, it's much smaller than the Earth, and it's much closer in perspective than what we've been taught.
Oh, okay. So it's like at a 45 or 30 degree angle to the disk?
It would be like if the disk is flat, it would be above as it rotates. And you see this this red line here?
Yes.
That's the equator. The top one is the Tropic of Cancer, and the bottom one is the Tropic of Capricorn. So if I make this go even faster, we'll see that the sun, let's see, we're August going into September, so that means the sun is should be heading towards the equator.
It's what towards the equator?
Heading towards the equator, so it's going to get closer to this red ring as we hit around September 20th.
So the disk is, let's say the disk is laying flat, right? The Earth.
Yep.
And the sun is like at a 15 or 20 degree angle to it?
It's directly above, so the angle would depend on where on the Earth you are, because the sun's so small. So if I paused it right here, which is the time of the current day, so you can see I'm here.
Right.
And so if I walked outside and I looked east, I would see the sun at like 40. What time is it? It's 9:30. I'd see the sun at like 25, 30 degrees.
Okay, but if the sun is directly above the Earth, wouldn't the whole disk be in light all the time?
Only if it was giant. It's much smaller. So if I had one room and I held up a candle at the top, yeah, the whole room might be lit. But if I stood on a football field at night and I held the candle up, the whole football field wouldn't be lit.
I see. Okay, I understand that. So you're saying the Earth is not at any angle to this disk. It's actually perpendicular.
The Earth is totally straight, totally still. It is the basis of everything that I understand, and I don't think it moves.
At all?
At all.
Okay.
Everything above us moves. We don't.
So the sun, okay.
All right. So if I jump it forward a month at a time here, you can see
the sun's getting lower.
Right. And then now we're in January, so the opposite's going to happen. It's going to come back towards the equator.
Right.
And it's going to come through.
Okay. And okay. The moon stays in the same.
The moon, let's watch it. So the moon is a little bit slower than the sun. So the sun chases the moon and catches up and overpasses. And as the sun catches up to the moon disappears.
Right. And that's what it's called, a new moon or a full moon.
Mm-hmm.
I mean,
new moon. Yeah, new moon is when the sun catches back up. You see it getting closer and it starts to disappear. And then we can also see the percentage. Which
the numbers around the edge of the hours of the day?
Yep. top. Oh, yeah, exactly. So that I can use it like a clock. Like if I just open the app, it'll tell me what time it is, right? So it's 9:15 in the morning for me.
9:15.
Yeah, so it's a 24-hour analog clock. So that's 9:12 at noon. Because I'm in Vietnam, it'll be straight down.
Right, but isn't that 9:10 or 9:09?
This is 9, and then this is the 10th hour, and it looks like it's halfway in between to me. So it looks like 9:30.
Okay. So the second hand is
this 30, yeah, exactly. This 30, 35, 40, 45 seconds. That's the second hand up.
So it's 9:35.
Yep.
Okay.
And then you can see the digital clock up here.
Okay.
So if we put the zodiac stars on it, you'll see what I mean, that right now in Vietnam, Leo and Pisces and Cancer and Justia are not visible because during the day, look how closely they move with the sun. So I'll never see Leo in this time of the year in Vietnam, just because it's daytime when Leo's above me. But so that is the cause for the slight shift that we see.
And you say that the stars don't move?
Stars definitely move.
Definitely don't move?
Do.
They do move.
They move above us a little bit, 4 minutes slower than the sun a day.
Okay.
The stars move 23 hours. It's called a Sodil day, where at 23 hours and 56 minutes, you probably remember that from your science class, where 24 hours isn't a true day. It's only 23 hours and 56 minutes. That's why we need leap days sometimes.
Gotcha.
That's not true. And if we thought about it as kids, we'd be like, wait a second. So if you take 4 minutes from every day, how come they all conveniently wind up in the middle of the day? It's not night in the middle of the day. That would be the truth. The sun moves in 24 hours, but it's also because the sun is moving in position through our sky, right? Like the reason why the sun is 24 hours is because the sun doesn't make a perfect circle. It makes spirals, because every time the sun goes around the earth, its track is slightly different than the time before, because the seasons are changing, and the seasons are always changing. Mm-hmm. So now you can see here that the sun is right on the Virgin Mary at noon, just the Virgin at noon. And because the stars are moving a little bit slower, and so if I jump by month, you'll see that where the sun is in relation to the stars does change by season.
Yes. Okay. So that's why we see constellations.
Yeah, that's why we see different constellations depending on the year. And then things like Orion, which aren't really represented in the zodiac, which are a little bit farther north, because their circle is so tight. In our North American sky, you can see Orion almost every night at some point. Not the same time, depending on the season. Like if I remember correctly, early summer, we can see Orion at like 7 p.m. But then in the winter, it's like 2 a.m. and then Orion's there.
I see. Huh. Okay, so here's another question for you. Mm-hmm. The Antarctica is an ice wall, right, at the edge of the disk? It
seems to be an ice wall. It does seem to be an ice wall, yeah.
It does seem to be. What scientific evidence is there to prove that it is or isn't?
It's not scientific evidence, it's literary evidence. So I haven't been there myself, and there's not exactly much recording. So I'm reading logs of captains, primarily Admiral Byrd from the U.S. Navy and Captain Cook from Australia.
And what do they say?
Well, Admiral Byrd writes that it's just insurmountably giant, is what he says. And he doesn't talk about it being flat versus globe. But he specifically mentions the fact that it's so big and it's so tall and it's so unforgiving and it's so hard to make landfall. And he talks about the wonders that are held there. So in an interview right in between the world wars, he talks about how the South Pole is the very last thing that has never been explored by man, and how every young boy today should be growing up with dreams of exploring this, because the secrets of the untold mysteries of the world are here, is what Admiral Byrd said. Captain Cook said it was good.
Oh, what about the South Pole expeditions and stuff that have gone? Supposedly, I mean, I'm not trying to contradict you, but they've gone from end to end of Antarctica.
Only one claims to actually have done that, and that's the one that's in the Guinness Book of World Records. And it's a pretty quick 20-minute probably research to tear that apart. So you find out that he's not an explorer by trade, he's a film guy by trade. And then you find out in his previous job, he got fired for faking dangerous situations in the middle of his documentaries. And then you actually look at his plot. And
his what?
His plot. The actual course that he decided to traverse. And if you draw it on a globe, it looks like he went around the outskirts. But then if you draw it on my thing, it looks like he just went to, he started here and then visited Antarctica, went about to here, flew here, went down, flew back, went up, flew here, went down, went back, went to New Zealand. He didn't even go all the way around the disk, because he never went to any parts of Antarctica here, and he never even claims to have gotten to the geographic South Pole. We make a confusion with people because we have what we call the ceremonial South Pole, which sits right on the edge of the ocean, and that's where the naval base is, and that's where the research lab is, and that's where the shiny literal ball is that you've probably seen pictures of. That's not the South Pole. That's called the ceremonial South Pole as opposed to the geographic South Pole.
And what about the North Pole?
North Pole is obviously real because compasses work. They tell us it's moving, which I have not been able to independently verify yet. That's kind of something I'm working on right now. Is the North Pole really moving? You know how when you're taught to use a compass and they teach the difference between true north and magnetic north?
Right. So what does it mean that it's moving, that the axis is changing?
Yeah, because I'm kind of looking at the Earth like it's a battery, and the Earth is a grounding plate, and that would kind of be like how the sun and the tides and the sun and the moon influence the tides. So a lot of what we understand and have been taught of gravity on the flat Earth model seems to need to be done by a type of electrical power. So there's something going on with the North Pole that's obviously the very beginning of an electromagnetic field, and it goes up and it surrounds the Earth as if the Earth was a plane, a tertiary plane in the middle. There's a really interesting writing done by U.S. Army research labs about direct energy weapons. And so they're talking about how to use direct energy weapons over a flat Earth, assuming the Earth is flat and you're assuming that type of magnetic field that I just described. So it's really interesting that they're using a line-of-sight energy weapon, and the paper begins with, this only works on the assumption that the Earth is flat. That got declassified in 2000, I think.
So the North Pole would be the positive pole, and the South Pole would be the negative pole? Is that what you mean by the battery?
I think the negative would need to be under the grounding.
Under the ground. So do we know what's on the other side of the disk?
No, the deepest that we've ever dug is 8 miles in Russia. It's called the super deep borehole. And like a video game, it literally just got too hard for us to mine. We just couldn't go anymore. And the deepest ocean, the Marina Trench, is only 7 miles. So like it's not that deep.
No. So what is your theory? What happens when we get to the other side of the disk?
I don't think we can. I think I think that we're confined in this realm from something that humans don't have the power to break through.
You mean the hardness of the rock?
Well, above us, I think there's a container above us as well that is called the firmament, is what the old word uses, is what the King James would use to describe it as well.
Right.
So I don't think that that's breakable. And so I would assume that something below us also would hit that level, whether it's just rock that gets super hard, like it seems the firmament isn't literally glass, even if it looks like glass, it can't literally be, or else in Operation Fishbowl, when we shot nukes at the firmament over and over, we would have broken it.
So have we done that? Have we shot nukes at the firmament?
Yeah. So Operation Fishbowl is in, like, you can search it on Wikipedia, where apparently we shot nukes at the very highest point that we could and exploded them in the ionosphere.
Yeah.
There are Army and CIA research documents that have been declassified that talk about experiments they're doing with the firmament. One specific that I could find quickly would be where they're trying to measure the brightness of the firmament. So it seems to me that Operation Fishbowl was probably them bouncing nukes off of it to test something. But that's conjecture on my part. I do know the Army has identified the firmament as something that needs to be testing, and I do know that the Army sent a bunch of nukes as high as they possibly could to explode in the 60s.
And nothing, and they couldn't get through, or what?
I mean, I think we'd all be dead if they could.
Oh, I see. Huh, interesting. So, you believe that I see that the moon here in your graphic here is round, or it's a 3/4 disc or something. Do you believe the moon is round? I asked you that before.
It looks, my own photography, and I'm going to pull up some of my own photography, but my own photography makes me think it's round.
Okay, round, but not a globe? Could it be a disc also?
It could be, because I really couldn't tell that from my perspective, but I'll be honest with you that my pictures make me think it's a sphere.
Okay, and what about the sun? Do you think the sun's a sphere?
Yeah, the sun looks like a ball of fire to me.
Yeah, so that's just your conjecture. That's not really any empirical.
Seeing the sun from a couple weather balloons makes me think that it's a ball. I'm more confident that the sun is the ball than the moon.
Okay, so why the well? What about like photographs of Jupiter and where you can see the storm, and then the storm rotates and it's not visible, and then it comes back around? Does that make you think that Jupiter might be a globe too?
I've been studying Jupiter for a couple months and trying to differentiate between amateur photography that's real and this digital conception NASA crap. Almost every picture on NASA.gov from Jupiter, they will say, is an image created from data. They don't even tell you it's a photograph. So I am still trying to convince myself, if that phenomena of the storm disappearing happens. I know the moons move. I can see the moons of Jupiter with my camera, which was really, really cool when I figured that out. That was just about a week ago. So I do know that the moon's changed position. I have not really been able to verify what that storm is. That's kind of what I'm researching now, actually.
Okay.
But if the storm goes away, like then it would appear to be spinning.
Yeah. So what your theory at this point is that the other planets in our solar systems very well could be spheres, but the Earth is definitely flat.
Right. In my terminology, I wouldn't say other planets, because I don't think we're a planet.
Oh, okay. So what are we? Just a disk?
We're a plane.
A plane. Okay.
Yeah. All right, I'm going to share.
What about while we're on this whole thing about the planets and stuff, what about Einstein's theory of relativity about bending light?
Yeah, so I actually got into that one quite a bit. So he made the prediction, and I studied the paper that was published on the 2017 eclipse with the stars, and there is is no proof to me that any of this is close to reality. And the main thing is because stars have what we call a wobble. You know, like they twinkle, right? We know that they twinkle. That's a phenomenon. We can argue about why they twinkle. And so a star's wobble is about 2 arc seconds. And it can go a single arc second in either direction. And it's unpredictable. It's completely unpredictable by very nature of the phenomena. And then Einstein predicted that the star's light would bend 1 arc second due to relativity while it's wobbling 2 seconds. And so lo and behold, during the experiment, the star did in fact wobble, but there's not clear evidence that it's light bending because of gravity or a star twinkling because stars do in fact twinkle.
Well, the way I read the article was that during a 1919 eclipse of the sun with the moon, through the corona, they could witness stars that they knew were behind.
Did you see the picture of them witnessing those stars? Because they had it in the article. Did you see the stars?
Yeah, there's a star. They print a red dot. They put a red dot where the star is normally.
Right, exactly.
And then they
draw the stars on for you.
And then they take a picture of where the star is during the eclipse, and you can see where the star is definitely much further to the left in the frame than it was before.
I mean, that would be far more predictable than the pictures that I've seen. I've only seen them have to draw where the star is and then superimpose it over images because they couldn't actually see the star. That picture from 1919 does not have any stars visible in it at all.
I wish I had kept the article. Like I could probably.
I've gone through it recently. I can probably find it in my history.
Yeah. So what about the picture here in the that you're showing me here of the moon? This is you filmed the moon here?
Yeah, this is totally me. This is not a scientist doing anything. This is just me. This is from my roof in Saigon. And so this is why.
Saigon?
Yep, I did this from Saigon.
I thought you were in Ho Chi Minh City.
Same city, different names.
Oh, I'm sorry. Right.
They renamed it after the war.
Right. So so can you tell from this the curvature here?
This right here. This shot right here. That looks curved to me.
Right. That looks very curved, but also it looks like it's getting darker as you get away from this side, right? You see what I mean? like right up here to the right, at the top right corner of the star right here. You could of the moon. I mean, you could see as the light goes around the moon from the sun, you can see how it curves around it. But you've already said that you believe that the moon is a globe, right?
It looks like one to me.
Yeah.
That's all I said. I don't really have beliefs about the moon. I don't know. I'm the first one to admit I don't know anything.
Why would everything else be?
Why do I need a belief about the moon?
Oh, I don't know.
Okay.
I was just asking you about it. That's all. Because
I don't have beliefs. I don't know. It looks like a ball. That's
okay.
All I have.
But let me ask you this: if all the other planets in the solar system are spheres, I mean not other, but whatever.
What does planet mean? Like where do we get that term? Because you're conflating. You're already going on the assumption of the heliocentric universe because you're like, well, if all the other planets are a globe, why aren't we one too? But planetos is a Greek word that means a wandering star. So you're not going to ask me if all the other stars are balls of fire. Why aren't we fire too? Because you understand that we're not a star. No thinker until the 17th century thought that we were a planet.
Hang on. That wasn't my question. My question is this. My question is, and I'm being honest, Joshua. I just want to know what you think. Everything else that we can observe from our our plane, if you will, is round as far as we can tell. Why would God or the creator or the big whatever make one disc? Is there any explanation for that?
Because we are not the same as anything else out there. We are special. We are the point. He created the earth and then furnished the lights above us. Just because the chandelier above me is made out of diamonds doesn't mean my floor needs to be too.
Okay, but
you see, you're totally going from a backwards approach, because you are, as you've been taught and as you've been trained, you're making this assumption that as you look out, you're also looking in. There is no reason to think that. So when you look up at the sky and go other, why do you think Jupiter is like us? Nothing about Jupiter looks like us. Nothing about Jupiter behaves like us.
I know, but you shouldn't get so emphatic when somebody asks you that, because that's what you're trying to disprove, is my theory, right? Or
no, because what I'm talking about is geodesy, and you're asking me about cosmology.
Oh, well, I don't know the difference.
Well, cosmology is the philosophical study of what the conception of the universe is, and geodesy is the scientific study of the measurement of the shape of the earth.
Okay, all right.
I've been studying the sky for years, and we've got ancients who studied the sky for their whole lives. And yeah, I've read their thoughts, but you're asking me if I've created beliefs without.
No, I didn't ask you that.
Well, I'm not getting offended or defensive. I'm explaining this so you understand my thinking. But you kept asking me, do I believe that the Earth is, the moon is a ball or a globe? And it's not how I do science, Zeke. I don't believe.
Right. But can you just humor me then? Just because let's just say that I, not just say, but it's true. I don't know anywhere near as much as what you have, because you've researched all that stuff.
Right.
But I'm just talking like man off the street here, okay? Like, I'm just going to present to you what I've been taught since, knee high to a grasshopper, and then I'm open to what you're saying, but I would ask for you to please just bear with me in my terminology and stuff.
I understand.
Huh?
I said I understand. Okay.
So the bottom line of the question I was going to ask you is, if you look out and you see, this looks like a sphere, this looks like a ball, and then your answer is that, God created the earth as disk because we're the center and we're special. I see it. I mean, this is just how I see this huge deviation from science all of a sudden to
you deviated to science because you went to cosmology, which is a philosophical study, Zeke. So you're asking me things about a philosophical study of cosmology, and I'm trying to tell you about my scientific study of the shape of the earth. So you're right. We did jump to faith because you asked me about cosmology, and if you keep asking me about cosmology, I'm going to have to stand on philosophical grounds.
Which is your faith, right? Philosophical grounds?
The faith, there's a line, because we're Christians, like, where philosophical needs to be superseded by theology, because I don't take that Christ is Messiah as a point of philosophy. That's a point of theology. I can't be wrong about that. I can't change. I can't evolve in my thinking about that. That's above me. That's outside of me. Philosophical thinking is very inside of me. But
I see.
That's how an atheist would describe it. He wouldn't see the difference between theology and philosophy.
I see. So go back to this whole thing about cosmology. Cosmology?
Mm-hmm. I don't. Cosmology, it's not my term. It's what the mainstream science was.
Right. So cosmology versus.
So there are two things. There's cosmology and astronomy.
Okay.
So astronomy is studying the phenomena of the stars. When will the sun rise? Mm-hmm. When will the stars move? How do the seasons change? That's literally looking up and studying and learning. Cosmology is philosophizing about what's out there.
Right.
Like that's.
Hang on a second. I'm going to turn the.
Okay.
I gotta turn the camera around.
Yeah, it looks like I'm at an Aquafina bottle.
Yeah, you're looking at an Aquafina bottle right there. So I gotta turn the camera back around.
I would think there's a button by the share video to do the swap, like to go back to the selfie.
By the share video?
That would be my guess.
Oh. Oh, let me see. I don't know. All right, I don't worry about it, I guess. I would like to switch to active speaker. What does that mean?
Oh, that's saying which camera is it going to show you on your screen. So if someone makes a noise. There you are.
Okay. Yeah. Okay. So.
These aren't my terms. I'm not making up any of these terms.
Right. No, I never said you were.
So astronomy is the study of how the stars move from our perspective. Because that is a scientific mathematical study.
Okay.
Cosmology is a philosophical study of what is the nature of our universe. What is it made of? What is out there? What is Jupiter? That's cosmology.
Okay. And then what is
Geodesy is the scientific study of the shape of the Earth. That's what I've been studying.
Okay. So everything else, as far as like questions about cosmology and that sort of thing, have just kind of like outside your purview yet?
I mean, I'm definitely still focused on them, but I'm not going to master cosmology in 2 years. That's going to take the rest of my life.
Yeah. Well, what about geodesy? Are you going to be able to master that?
I mean, if I had $100,000 and I could run my tests, I think I would get to a point where I'm certain. So yeah, I think geodesy has a clear endpoint. Then there'll be different parts that aren't so much geodesy, like where does the Earth end? What is Antarctica? Where's the firmament? Right? But that won't be specifically a scientific study on the shape of the Earth. That'll be more a natural study discovering the nature of the Earth. But if I could run all the tests that I've got in my mind right now and I had the funding to do that, I'd be able to publish.
So this whole study of yours started a year ago or 2 years ago?
About 2, yeah.
Okay, and it all started by the student or this classmate, colleague, whatever, asking you to prove that the Earth was round.
Yeah, she watched a YouTube video and was confused. And
the more you tried to prove that the Earth was round, the more you realized the Earth was flat.
Yeah, well, it wasn't that easy. I didn't want to be a flat earther. See, this didn't happen like this. I went kicking and screaming into this. The more I realized that everything they told me was a lie, and
you could prove it was a lie.
I couldn't prove it's a lie in a court of law beyond reasonable doubt, but I think I could persuade a jury of my peers that it's a lie. But I'm a very persuasive speaker.
Yeah.
So, like at the end of the speech that I gave for my academic director, my colleague last week, and he didn't say much through the whole thing, but he was taking notes furiously. And so he closes his notebook and he looks at me and he goes, "Well, you're certainly a good public speaker."
Right. I remember you saying that.
I was like, well, that's not really
let's
the reaction.
Let's talk about can you show the slide that has the your goals again?
My table of contents?
Is that what it was?
Are you referencing my debate?
I'm not sure. It just had different bullets that showed
Is it one I've showed you now, or is it one that you saw on YouTube?
Here. This is it. Okay. So we've talked about the introduction. We've talked about heliocentrism, right? So
we're not into heliocentrism yet.
Oh, we're not? Okay.
We're still talking about my methodology. We're talking about how I study, why is my study sincere, what the scientific law is. And so here I'm giving examples of scientific laws.
Right. This is These are not refutable.
Nah, they're not. They happen all the time. And then these are our mainstream theories of why each of the laws happens.
The Earth rotates on it, so you say that the disk is turning?
No. This is the mainstream. This is not mine.
Oh, this is okay.
It is the mainstream theories in the heliocentric model.
The heliocentric model.
That's the one that normal people believe in. Heliocentric means Helios is the Greek god of the sun.
So, okay, so everything rotates around the sun.
Yeah, exactly.
And what's the name of your theory?
Geocentric. Everything goes around the Earth.
The Earth, right? Okay.
So this is the heliocentric. This is if I search Wikipedia, why does the sun set? The sun sets because the Earth rotates at 15 degrees per hour. Right. Why do the seasons change? The seasons change because the Earth is tilted on its axis at 66.6 degrees. And the eclipses, what causes the eclipse? The mainstream answer is the Earth gets between the sun and the moon in a lunar eclipse, and the moon gets between the sun and the Earth in a solar eclipse.
Right.
The phenomena that explains the stars in the heliocentric model is the stars and the suns and our sun is exactly the same, except the stars are farther.
The fixed stars are suns at a great distance, right?
That's what we're taught, right?
So what did you say? What did you just say? That the stars and the sun are
the same thing in the heliocentric model. By nature, they are the same. One's just much farther from us, and that's why they look different.
Right.
That's what we're taught. And the sun and the moon appear at the same time because the moon is 400 times closer than the sun, and the sun is 400 times bigger than the moon.
The moon is 400 times closer than the sun, which is 400 times bigger than the moon.
That's why when you go out, both the sun and the moon look to be about the size of a quarter. Like in the heliocentric model, the sun's infinitely bigger than the moon, right? 400 times bigger. So why do they look the same size? Well, because the sun's 400 times farther away.
Got it. Okay.
So what I'm saying here is my method and my studying is all based on the scientific method. I observe the phenomena. I question what makes it happen. I hypothesize about that theory. I design an experiment, and I make a prediction of how the experiment will go, and I do that experiment. And the process repeats itself. Everything about my study has been focused around this and about a scientist specifically who can design and predict and do the experiment. Newton gives us neat little experiments about how the bending of the light of the star, and it's not something that I can design and do over and over and over. I need an eclipse that only happens once every 18 years, 11 days, and 8 hours. And even then, on almost every single eclipse, the conditions aren't right to see it. And every picture I've seen of it, I don't see the star there. So we've got, I will trust any scientist who's going to give me experiments that can be reproduced by anyone and everyone.
I see.
And so now we get into heliocentrism. And now I could start to pick apart the mainstream theory in the same way that you can show holes in my understanding of my cosmology, because we are taught this mathematical law like it's a scientific one. We're taught that big G is this number, 6.673 times 10 to the negative 11th power times Newton squared meter, multiplied by square meter towards the negative kilogram squared. Like this number that we use in all physics and theoretical physics equation, we are taught like we understand gravity so well that we could launch a man to the moon. And we're taught that it's a law, and most people think that it's a law because that's a mathematical law, because that's how math works. You can make laws up in math. You can't do that in science. It's unobservable, it's unverifiable, it's unpredictable. There's no experiment that's going to give us, and it is a constant just because that's how math works, but it's not a law. But we do know that things drop, right? That is the law. The phenomena is that things go down. And this number and this concept of gravity is required for everything about heliocentrism, because if you ask me what makes my sun move above the earth. And I'm like, well, it's some kind of electromagnetic power, but I don't really understand it. And I ask you, well, what makes this earth move around the sun? You're like, well, it's some kind of gravitational power, but I don't really understand it. So we are in the same thing there. So Newton made this prediction that objects of mass attracted each other. That's Newtonian gravity. Nobody thinks that's true anymore. Nobody. There's not a human being on the planet except fifth grade children who believes that objects of mass send out waves through the ether and attract each other. We do observe that things more dense fall to the ground, and our question is, what holds us to the ground, or whatever, or the water, or whatever we're on top of? Newton's hypothesis was that objects of mass can attract each other. So how do we test that? I should be able to drop a penny off of a cliff and see that penny fall on an arc because the cliff's mass is attracted. I should be able to bring objects of mass other than the earth and see them attract each other. And people have tried to do this experiment because once upon a time they believed in Newtonian physics. So there's this man named Henry Cavendish and his great balls of lyre. And this experiment is pure ludicrousy. He built this contraption in his barn, and then he went 100 meters away and watched it through a telescope while he drank himself to sleep each day and pretended to take notes, but he wrote down no math. Here's a better way to see the same experiment. This is his actual illustration, but here's someone drawing it with a little more artistic ability. So he's got these giant boulders, which were literally the biggest boulders that he could find. And then he's got these little tiny balls that are suspended on a rod. So the balls are connected to the rod together. He then hangs that rod on a string and tries to get the two balls to swivel back and forth between the big balls. And that's the extent of the experiment. And they still claim that this is, if you hit YouTube, how do we know that gravity is real? There's still a guy who's going to go back and tell you about this experiment, even though the experiment didn't give us 6.673. Not even close. And when students do this, which they tell you, students do this experiment all the time. Yeah, they literally do, but they never, ever get the right number. Their teacher says, good job, now fix your G. Over and over and over and over, because what is the actual prediction in this experiment? Yeah, I think I said all this. Yeah, is it that G is our mathematical formula? Because that's failed. Is it the balls swing at all? Well, the truth is, most of the time people do this experiment, the balls do swing. Most people can get it so that the balls swing. If this experiment is the end-all be-all and it really does measure gravity, shouldn't NASA be running this experiment in the most perfect vacuum chamber with the most perfect conditions over and over and over and over and over to correct their understanding of the mathematical constant if this experiment was a validity? Why is the number always wrong? So the argument pretty much is that the prediction was that the balls would swing at all, but there's so many variables that we couldn't possibly know how much the balls would swing. I have severe problems with this because I very much believe that if I hang a rope that's thick enough from the ceiling, I could make those balls swing back and forth based on the tension of the rope without the giant boulders. And I've done this a few times. It's possible to repeat this experiment without the boulders. Oops. So it isn't gravity. It isn't objects of mass. I've actually never done the experiment with the boulders. I've only done it with without, because that was my whole point, that I can get the balls to swing without. So since I'm calling this a sincere study, I gave it as my right, and we were talking about this a little bit yesterday, to dismiss all priori arguments in favor of a posteriori. Now, this is a philosophical term. A priori means an argument that you are bringing based on an assumption or something prior. Hence the priori. So you have accepted a truth, and now you're walking around trying to deduct things from that truth. And posteriori is saying only things that I have witnessed and only empirical evidence that I've seen will I take all that evidence and instead try to compile that truth, as opposed to assuming I have the truth and going the opposite way. So I just wanted to know if there was a single phenomenon that from my own observation could prove we orbit the sun instead of the sun orbits us. That was like the first year of my study. It blew my mind in actuality that there isn't. And I'm going to read here a quote by Dr. Ellis. He's a magnificent cosmologist from South Africa, and he's also a lecturer at New York University of Astronomy. And he wrote an entire paper in 1998 published just on this quote and the topic that I'm talking about. And it's the fastest way for me to sum up my research is to really just read this man's quote because it's perfect. People need to be aware that there is a range of models that could explain the observations, Ellis argues in Scientific American in 1995. For instance, I can construct you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on observations. Ellis has published a paper on this. You can only exclude it on philosophical grounds. Now, Ellis is a cosmologist, so he goes on to say that in my view, there is absolutely nothing wrong in that, because he's a philosopher. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models, and a lot of cosmology tries to hide that. Everything you've been taught from childhood tries to hide that we assume we orbit the sun based on philosophical grounds.
Okay.
No one has ever told you that in any of your science classes. Because if you told students that at 5 years old, the students would stop believing in gravity very quickly because their critical thinking would hit again. Like, this is all bullshit.
Let me stop you for just a second so I can understand something.
Mm-hmm. I need to get some more water too.
What you've been trying to prove here, since you showed that equation, was that in order the model that you showed with the four balls, the two larger ones and the two smaller ones, was to prove or disprove. Yes, that was to prove or disprove the equation. Is that correct?
The experiment existed years before the equation, hundreds of years before the equation. So the experiment was originally created to prove Newtonian gravity. In science, physics, college textbooks, they use this as a proof of, believe it or not, Einsteinian gravity, because their students don't really understand the difference.
This doesn't make any sense. Why would they use that?
It doesn't.
The
it doesn't make any sense.
mass is what produces gravity, right?
But that's the point, right? That's the point of this experiment, is these giant balls should create the mass that makes the middle ones swing.
Well, no, but they're not rotating. They're not.
They don't need to rotate for gravity. They just need to be mass.
Well, that's not how it works, though. The rotation of
According to whom?
To me.
Okay. Okay.
According to me, because as far as the way I understand the theory of relativity is that mass, there's three things in space: light, time, and mass trumps all three. Or mass is the same as gravity, because the bigger the object, the bigger the spinning of the object creates more gravity. Therefore,
no. So spinning has nothing to do with it.
It can bend light. Like, for example, the Apollo 13 mission, when it needed to get back home without any fuel or very low fuel, they swung it around the moon using the gravity of the moon and the rotation of the moon to slingshot them back around towards Earth. That's a good example of mass. The bigger the mass, how about a black hole? A black hole has an incredible amount of mass.
Why do you think those are real? What experiment or phenomena has been observed? There's a part in space that we can't take pictures of, so you assume it's the biggest thing in the universe? That's insane, Zeke.
Hey, hang on. Time out, Joshua. Remember what the conversation we just had a minute ago, okay? I'm just coming from what I've been taught, okay?
Okay, but just so you know, Zeke, most mainstream astronomers don't think that black holes are real. Like, that is not accepted science at all. No one would say 100% black holes are real. No educated person.
But that's I never said that they were 100% real. I'm just saying you're
But you're trying to use examples of
right.
articles that you've read instead of phenomena that you've observed. So
I can't observe it because I've never been an astronaut. But see,
no
it's
one
very
can
difficult.
observe the black hole. That's why we call
But
them
see,
black
it's very
holes.
difficult to speak with you because the problem is that you go straight for the how can I say it?
Kill shot.
Yeah, that's a good way to put it. But it's not really a kill shot. You question the basis of of the belief or of the theory and where it came from.
Sure.
Okay.
Of course.
Okay. Yeah. Yeah. And that's great. That's great. But what I've asked you to do, and I'm sorry if I didn't communicate it rightly, but is if we could just take that as a given, just for the sake of our argument.
Well, that's why
say,
I asked you. That's why I asked you describing gravity according to whom, and you said according to Zeke. And the truth is, I don't know much about Zekean gravity, and Newtonian gravity and Einsteinian gravity stand in opposition.
Right.
They are not even close to the same. All right. So now you're asking me about Einsteinian gravity in this experiment, which makes no sense because this experiment was designed to prove Newtonian gravity, which is my whole point. It makes no sense. Right. Even from a mainstream science point of view, it makes no sense.
Right. And I agree with you, but I was just trying to explain to you how I understand gravity, which is the more density of the mass, that's what creates more gravity. Is that Newtonian or is that Einstein?
Density doesn't have to do with it. It just has to do with how much mass is there. And obviously, if it's denser, more mass can fit in the same area. So there's no part of density that has to do. It's only mass, and it has nothing to do with rotation. And they're both of them believe that mass creates this. But Einstein thinks that gravity is a instantaneous bend in space-time, where Newton thinks that gravity is a wave that radiates from a large object of mass to another.
Right. No, see, Newtonian isn't correct. I adhere to the Einstein theory, obviously.
So if in my understanding of Einsteinian gravity, and this is a lot of conjecture, and I could be wrong about this, and I'd be interested in other people's thoughts, is I believe the balls should hold still. Because in Einsteinian gravity, all the effects of gravity are instant. In Einstein's theory, if you removed the sun, it would take 8 minutes for the light to reach here, but our absence of that bend in space-time should be instantaneous. So as I understand the propagation of the space-time around these giant balls, I think the two balls on the sticks should come to a middle point and then hold still in Einsteinian gravity.
Say that again?
I think in Einsteinian gravity, because the bend of the space-time is instant, that the balls should come to a middle point and then hold still. As they're two opposing bends, instantaneous bends, unlike the Newtonian where the waves can ripple and fight, and then we see this go back. So in Einsteinian, boom, it should just be finite.
Just so that we have an understanding of our conversation, I'm not saying this like as a negative thing, Joshua, but you say this is my conjecture or this is what I believe, and it can't, I didn't have any scientific proof for it. I would ask you to allow me to have that same caveat too, because it's just things that I've observed, things that I've read, that kind of thing. I can't really seriously prove scientifically what I believe, but this is what I've been led to believe.
I understand, but a lot of what I'm trying to do, Zeke, is I'm trying less to convince you that the Earth is flat and more to get you to analyze why you accept that belief. So I'm attacking those not out of attacking you, but because I want you, even if you don't articulate it aloud to me, I want you at least internally to think about, wait a second, why do I believe that?
Well, let me explain to you why I believe black holes exist. One of the things that I've observed with, and of course you can always argue with the validity of the video or the validity of the people who put it out or whatever. But astronomers have observed large masses of large mass suns, okay, that have that when they orbit or when they rotate, they wobble back and forth, and that leads them to believe, because, and we're talking about a sun that is maybe 100 million times bigger than our own. It's huge, not giving your flat earth theory that the sun is a lot smaller and a lot closer. I'm just talking in the regular cosmology, if you will. Mm-hmm. So these planets, these huge suns are wobbling in their orbit, which leads them to believe that something of great that something of great density is yanking them sort of a little bit at a time from their orbit. Yeah. The only thing that would be big enough to yank them like that would be a black hole.
Something is yanking them a little bit from their orbit, but not a single position of a single star has changed in 10,000 years of recorded human history.
Right, but you can think that can still hold water within that theory.
That's insane. So let's
no, wait, hang on a second, because if the star is the star is still in the same position, it's just wobbling. That's all. You see, it didn't yank it out of order. It just wobbled.
Yeah, it twinkles. I know that stars twinkle. I don't have a problem with that. What we call that exoplanet discovering star wobble, which first was discovered in the 1990s from a spectrograph. Let me remind everyone here that this is not an observation that has been made by eyes. They used a spectrograph to record this. So a spectrograph is a giant light bucket that records light as numbers. And they're like, hey, look, this number goes up sometimes and then comes back down sometimes. Literally anything between the star and the telescope's light bucket could create this disturbance. A bird could have flown across, a cloud could have gone across. And then these Swedish scientists who were hunting for exoplanets used this to prove that they found an exoplanet, then publish a paper that a computer scientist takes, who then writes the new program for all cosmologists in the world to identify when there's a star wobble based on this one unprovable theory from these two Swedish cosmologists. And now the young cosmologists don't even see the spectrograph. They don't even know the numbers that are changing. They just see a computer program that goes, hey, buddy, you found a planet. And that's all it is. And I'll refer you to something that you absolutely should watch. And it's just a documentary on the discovery of the first exoplanet. And
what do you mean by exoplanet? You mean a black hole?
No, an exoplanet is is a planet not in our solar system.
Oh, all right. But
so that is the foundational theory. That is where star wobble was first coined, and they are found through star wobble, and it is the origin of that theory. I don't actually know offhand any stars that wobble because of black holes. I don't doubt you saying that there are some, but most stars wobble because of exoplanets that orbit them. That video, that video explains it quite well, and they go out and have beers. It's a quick 5-minute thing. It's hilarious. Like these are the guys who discovered the planet.
Think about black holes. Give me your thoughts about this. All right. So if you take incredibly accurate clocks, right, mm-hmm. and as the clocks are being put in a tower higher and higher and higher, the top one will be. Let me see.
Yeah, that's a theory. I don't think that's ever been proven. That's Einstein's theory for sure.
Yeah. It hasn't been proven because we can't build a 100,000
clock accurate enough, I think, right?
Well, 100,000 story building, but the idea is.
Well, why couldn't we do it on a plane or a balloon?
What?
Shouldn't we be able to prove that theory by sending the clock up in a balloon?
Well, but.
Or is it just not high enough?
I guess you could, or a rocket that goes at the speed of light back and forth. See, the whole idea is that the density of the mass, the density of or I keep saying density, but I know you're not saying it's density, but the mass,
the quantity of the mass,
the slower the time goes.
Yeah, I guess that is true. He doesn't really. Yeah, no, I guess that is true in Einstein's theory.
That reaction.
Yeah, well, yeah. I think everything's being recorded. Yeah, it is.
You see, that's the whole idea behind the incredible amount.
They make that point. What's the movie? Interstellar. They make that point where they're on the planet and they're like, 1 hour is 7 years, right?
I don't know. I didn't see that movie, but the idea.
They do lots of relativity experiments.
So going back to his original theory, Einstein's theory of light, time, and gravity trumps all three. So that's why we know that there's something out there
gravity
that
ripples through all three.
Huh?
Gravity ripples through all three. I wouldn't say it trumps. I don't really know what you mean by trumps.
Yeah, because gravity has effect on the other two, on light and time.
Yeah, but it has an effect on light, and it doesn't. I don't think. I guess it has an effect on time, but space-time would be the medium in which gravity propagates.
Right, but the more density or the more mass an object has, the more chance it has to bend light and slow time down.
That would be a more quantum understanding of relativity if you're saying the more chance it has to bend things and slow time down. But Einstein's famous for saying gods don't play dice. He absolutely disbelieved everything about quantum mechanics. He's like, there are variables that you haven't found yet. There is no random. Einstein was very much against Heisenberg.
Very much against what?
Heisenberg. Heisenberg is the founder of quantum mechanics, more or less.
He didn't like the quantum mechanics theory?
No, he's very famous for saying gods do not play dice. And that was his end of it. He's saying if things are random, it's because you don't understand what's happening. They just look random to you.
Yeah, but quantum physics isn't. Well, you're talking about string theory or super quantum physics, right?
I don't know very much about string theory. I know more about quantum mechanics. So that would be
mechanics. Yeah, but I think you're talking about super quantum mechanics where it's random, like the string theory idea, where everything is interconnected, but it's all random and it's happening all the time.
I have never heard of a single branch of quantum mechanics that isn't random.
Right, but see, these three things about quantum mechanics are not, and they've been proven just because of the fact that
they're not about quantum mechanics. Like you're talking about a theory that predated quantum mechanics by 50 years.
Well, to me, it's been explained to me as quantum mechanics, and it only happens in space.
Of course.
I mean, I don't know. I could be wrong.
Yeah, it only happens in space, so you can never see it.
Right. But it's been observed, I guess, by other people that I can't verify. So
you'll find Zeke, if you deep dive on these things, your mind has made their stories way more convincing than they actually are. If you go back and you look for there's a guy that most globe earthers quote named Aristophanes. He's a Greek guy from 300 BC who did not exist. Like absolutely did not exist. The very first. He's a fake man. He's a legend. The very first time he's mentioned. Yeah, they made him up. In 1840, he was made up in a book. And then there are hundreds of thousands of articles online about this man. Some of them even written by artificial intelligence about this man using sources that use the source that use the source that use the source that use the source that use this original book in the 1840s. And so if you go, look, there's 100,000 articles that prove Aristophanes was real, and I just go, like, I'm not tagging you, but like, what's their source? What's their source? And you're like, oh, all 100,000 articles point to the same book that was written in 2010. Oh, this book in 2010 references a book written in 1930. That book referenced in 1930 references a book in 1840. That book has no bibliography, and it's a fictional story.
Right, right.
And then you're like, oh, why do I believe this? Wikipedia told me 100 times over it was true.
Right. Well, let me ask you this, getting back to the whole density, okay? Uh, what do you think of that idea that the closer you get to a dense object, the time slows down?
I love it because it should be an experiment that you can make a prediction of and do.
Well,
I should be able to send something up by a Skype. Well, I don't know the math off the top of my head, Zeke, so I'm going to guess in reality that the mainstream answer, if I was talking to a theoretical physicist asking him if I could use a balloon, I'm going to guess that they would tell me that there's no oscillator on the planet that can keep time accurately enough. So my experiment would be invalid.
Well, why can't you keep a clock, like let's say an atomic clock, on the ground?
Because atomic clocks don't keep time, Zeke.
What do?
They reach out for data and update their time over and over and over and over and over and over.
Well, whatever.
That's why they're accurate. It's called an oscillator.
Whatever the most accurate clock we have.
It's called an oscillator.
Okay,
it's a diamond that they shine light through, and they see how long it takes to get the light back.
Okay, so you use that, and you figure out what time it is on Earth, and then you just send the balloon up, come back down, and see if it's slowed down.
So I would need to do the math before I spent $5,000 on a weather balloon. Obviously, here's my gut feeling on this, and then I'm going to go to get water. My gut feeling is that either this has been done 100 times, or the mainstream answer is the change of time is so insignificant we can't observe it. That's going to be my guess.
That would be true, but there would be a change. But it would be so
right.
small.
But if it's unobservable, I'm not going to spend the $5,000 on the experiment, right?
Right. But I'm just talking theoretically. I'm not talking that you're actually going to do it.
Right. And so when we're in thought experiments, there are all kinds of ones that we can do, and they interest me way less than ones that we can actually do.
Well, what about an astronaut taking a watch into space?
I mean, I don't believe in space, and I definitely don't believe in astronauts. So.
Well, I'm just saying, bear with me here. Just, humor me.
I still think in the mainstream that the ISS would not be far enough away for us to observe that change in time. Unless, there's something else, though. It's not just about mass. You can also change time dilation by speed in Einstein's theory, right?
Right.
Once again, I don't think we've got anything that even in the mainstream can come close enough to the speed where it's observable. The ISS is moving at 17,000 miles an hour relative to the Earth.
What's ISS again?
International Space Station.
Oh, International Space Station, right.
Yeah, so
do you believe that? Do you believe that is up there? No.
I don't believe people live there. You can see the lights sometimes, and if you're not in a communist country that doesn't have the right treaties with America, you can see it past the moon. But for some reason, even when the ISS flies over Vietnam, it's not visible. It is the second you cross the border into China, even if you go 10 feet. But it's not ever observable a single time in the history of the world in Vietnam.
Why? Why do you think that's?
Because they're faking it somehow. And I've got math to explain why that I think they're faking it, because when it traverses the moon, the area that can actually see it is too small. It should be a much bigger area for how high they're saying that it is. So I think they're faking what we observe as the ISS in a way that I don't understand. A lot of conspiracy theories think that it's a projection, so it's actually something done from land projected up there. That seems so difficult to me. I would think, why not just send a balloon up there, man? That's way easier. Just make it the right shape. So I don't really know. But I do know on the ISS tracker, I can track the ISS going over Vietnam. And then on the ISS locator, which tells you where you need to be to see the ISS physically, even when the ISS goes over Vietnam, there is no place that's visible from Vietnam. But right on the border of Laos and right on the border of China and right on the border of Thailand, instantly it's visible again.
Interesting.
Fair.
And you have observed that.
I've been trying to see it pass for 2 years. So obviously I haven't literally checked every day, but I've consistently been checking if I can ever see it in Vietnam for 2 years.
Very
And
interesting.
if you checked your spot, like where you are in America, you should have one within a month.
Right.
And you'd be able to get your camera out and set your camera up to your computer so your computer takes the shot. And then the second the ISS goes in front of the moon, the camera will take the shot and you'll see the shadow in front of it.
Right.
And I've seen tons of amateurs do this on YouTube, so I very much believe it's possible, even though I haven't done it. Tons of amateurs I've seen do it.
Right, let me get you water. I think my dog wants to go outside.
Oh, okay, cool.
All right. Well. You probably can't see me, can you?
Let me check. I can a little bit.
Yeah.
There's some lighting there. I want to look at this real quick. So when I was out there, I just looked it up.
What time do you have to go to work?
Actually, I do not work today.
Oh. You're a professor, right?
I'm a teacher, not quite a professor. I need another 10 years or so. But I don't have many classes right now because we're end of the very short summer break that the children got for Corona.
Mm-hmm.
So I've got a pretty relaxed schedule this month.
You still get paid though?
No, I don't, but that's because I'm switching schools. So that's my own doing. All right, I got this picture downloaded. Here we go. Okay. I want to show you this to continue my to make my point about a lot of this evidence is way more convincing in your mind than in reality. And I said that earlier, and I want to stand by that. So this is where my screen share. Right, this is that picture. Right. This is proving that Einstein's right. This is the 1919 eclipse where you can clearly see the bend of the star.
You don't believe this?
I don't see a clear star, Zeke. I don't see a clear star. Nothing on this page even looks provably to be a star to me.
Right there. What is that right there? I don't know. I can't point.
You should actually be able to draw on the screen. There should be a thing that says annotate.
Annotate?
Mm-hmm.
Oh, right here. Oh, no. Okay. Oh, sorry.
Looks like you got it, though.
Yeah. I need to move the picture up a little bit. Ah. There it is. Whoop. Hang on. How do I move this bar down?
I don't know. I'm not super familiar with the phone controls.
There it is, right there. There's a star. There's a star. Those are two of the ones I can see that are visible. You see them?
Yeah, I do see them, and I've had those outlined as stars, and I've had people try to point out that that's a star, and then that observation is a star, and that's a star there.
What is this here? What is this here?
Which one? I've had people try to tell me that that is supposed to be a star coming through the corona, because remember, that was actually Einstein's prediction. If this was the star in question, since this is about 10 arc seconds away from the sun, the wobble wouldn't even be noticeable by our spectrographs today, let alone by the naked eye.
Just to be clear, when you say wobble, they said it was actually a different position.
Okay, so They say that, but like, so they did this experiment again. Harvard just did it, and I spent a massive amount of time poring over this. I don't think my screen's still being shared. I'm not sure. Oh yeah, it's the other thing though. And I haven't found the exact paper, but I just found the abstract. So I'm going to throw this link to you as well. Usually the papers are behind a paywall, but with enough Googling, you can find them. I'm trying to pull this up. So yeah, you're right. It's not a wobble. I'm calling it a wobble because when the phenomena is observed, it's not differentiatable. The theory is that the cause is different than a normal wobble. So in this experiment, maybe this is the paper. Maybe I'll get lucky. No, that brings me back here. So in this experiment, they go on and they look for a movement of 1.71 arc seconds with a margin of error of 1 arc second. And the star that they were looking at naturally wobbled by 2 arc seconds. In the actual pictures that they show, and like I said, I've dropped the link. I will find this and I'll send it to you. In the actual pictures they show, just like Einstein's photo, I do not maintain that the stars are clearly identifiable as having moved, and I don't see an identifiable prediction of where they should be, except done by a computer simulation. They don't actually have a picture of the star before the sun, or yeah, I guess they couldn't do that. Fair. They would have had to start their experiment 6 months earlier to be able to do that. But still, they should have done that. They should have had a picture of the star at the exact same time on the turn of the parallax. And they did this in 2017, and they published in 2019. And if this phenomena was so observable by the naked eye that all the men in the world looked up and said, Einstein was right, why the fuck didn't they record a video of it?
Okay. Point well taken. One of the things that
it's a sore spot for me.
I can tell. One of the things that they said about the original experiment in 1919, right, is that they said that there is a constellation of stars that is visible, or that they had already plotted. Do you remember that part of the article? They said something about the
article or the paper. I read Einstein's paper.
Yeah, well, he was already passed away then, wasn't he, in 1919?
No, he redefined his theory of relativity in 1924. Redefined.
Right. No, you're right. No, but anyway, they had some kind of constellation or something. I can't remember exactly.
A constellation, a zodiacal star?
Yeah.
Are you sure it wasn't a cluster?
Yeah, maybe it was a cluster.
Okay, that would make more sense.
So if it was a cluster that they had already mapped in the sky.
Right, that is the point. My point is, well, I've got a couple of points. So remember, how much the star should bend should be directly proportionate by how close to the sun that it is. So if these are the stars, there should be no bend because how far away from the sun. Remember, the expectation was that he could see a star inside the corona. This is the corona, right?
Right.
So he said that somewhere in the red, we should see something that normally would be in the yellow. And, all right, so there are some arguments that, hey, maybe that guy's a star. Hey, maybe that weird line thing's a star. Hey, maybe that weird line thing's a star. Or maybe it's problems on the silver nickel photograph from 100 years ago.
Right.
So here's the thing that people really start to play mind games when they write modern articles. And I don't actually know if it's purposeful because most journalists don't understand crap about the movement of the stars. They don't understand what an arc second is from their point of view. But remember, I said 1 arc second in either direction is how much a star would twinkle. So if you look up, and I don't know if you can see stars. It sounds like you can hear crickets. So I would hope you can see stars.
Oh, there's 1,000 of them out here.
Oh, wonderful!
No.
Are any of them twinkling tonight?
Yeah, yeah.
So that movement is about an arc second across.
Okay.
This Harvard experiment in 2017 was trying to track a movement of 1.7 arc seconds. I have a severe problem with any men saying they observed this phenomena beyond reasonable doubt, especially ones who all went in with the pure intention that to prove Einstein correct. It is so small, and it is such human error. And in 2017, they still don't bother to give me a video? Come on, man.
Yeah, I see what you're saying. I understand. But explain to me why bending light would disprove, or prove, or what does that have? What's the direct correlation? I think I know what it is, but what's the direct correlation between that and the Earth being flat?
Well, because if gravity is real, the Earth can't be flat.
Okay, so, but you know that something's holding you to the ground.
Yes.
Okay, so what is that? If that's not gravity, what is it? I'm just being honest. I just want to know what you think.
I think it's more similar to electromagnetism than it is to objects of mass. I think it's more about an electrical charge. And so the question.
But so that leads us back to the same. I'm just a little confused because you said the Newtonian theory of gravity. Nobody believes that.
No, I mean, I guess actually my theory of what holds us down is closer to the Newtonian theory of gravity than it's not. You know what I mean? I just don't think mass is creating it. I think it's electrical charge that's creating it.
Okay. There's no way that the other side of the disk could have enough mass to produce that gravity?
I don't see evidence that mass attracts. That's my problem. I don't see any evidence that mass by its nature attracts. My penny down a cliff is a very real problem I have if we're in the world of Newtonian physics. I understand that Einstein answers this question already perfectly.
But you're saying that gravity is an electrical wave. Isn't that what Newton said?
He did not think it was electrical. He did think it was a wave.
So what kind of wave did he think it was?
I don't know that he gave it a name. He only described the medium in which it propagated that he called the aether. I don't believe he
called it the what?
The medium that it went through, he called the aether. I don't think he gave the name of the spectrum that the wave was on. Like we have acoustic spectrum and we have electromagnetic spectrum for sound and for light. I don't think he coined a term, but maybe that's just my own ignorance and maybe he did.
Okay.
But I think that whatever's holding us to the ground shares properties with the electromagnetic spectrum. And you're going to ask me, but why doesn't metal fall faster than non-metal? And one, I don't know that it doesn't. Some flat earthers are about to spend 50 grand on some equipment to test if any of that could be true. It'll be cool. But it could be just a different propagation of the spectrum that doesn't have a bias effect towards metal.
Getting back to your statement that if gravity is real, the Earth can't be flat. The premise there is that because it being flat, they wouldn't have enough mass.
Don't by nature all bodies in space in the heliocentric model turn into spheres because their own mass caves them in on themselves?
Yeah, that's basically the theory behind planet formation.
Yeah, exactly. So if gravity is real, I don't have a problem with the theory of planet formation if gravity is real.
Okay, so if gravity is real, then, but it doesn't apply to Earth? Is that what you're saying?
No, I'm saying if gravity is real, then we probably live on a ball.
Oh, I see what you're saying. I see what you're saying.
Yeah.
But still, it's very difficult for you at this point, except for conjecture, to say that gravity is not about mass. It's about some kind of electrical wave.
Sure, that's pure conjecture. The affirmative statement I'll make is no human being has proven gravity is about mass. That's my problem with their theory. Especially, and I get this biasy a lot because I've been taught so long that it was proven beyond reasonable doubt that as soon as I realized that scientists argue about it, I go, why did you have to lie to me and tell me that that was so true when the real brilliant guys are still arguing about it? And so that irritates me, and I tend to dismiss things quickly because of that.
Right. Let's go back to your statement that you said that objects with more mass will fall faster than, say, a rock would fall faster. True. A rock will fall faster to the ground than a feather, won't it?
Not in a vacuum chamber.
Well, we don't live in a vacuum. I mean, I'm just talking about.
Okay, sure, but I think we both have a pretty solid understanding of air resistance. So I mean, I don't think we have any disagreements about air resistance.
Air resistance.
Right. That's why the feather is going to fall slower than a rock, is because air resistance. The air will hold the feather up. The density of the feather is not sufficient for it to slice through the fluid being air quick enough. Much like if I drop an apple, it will fall, not forever, but until it hits water, and then it'll float.
Right. Or if you drop it over ground, it'll just hit the ground.
It'll hit the ground, yeah.
Yeah.
But the ground's not a fluid, so that was why I went to water, because air and water are both fluids.
I see what you're saying. Okay.
So obviously, if we look at plastic, we know that solids of much less density can fight gravity, for the lack of a better word. But fluids only can fight gravity depending on their density, right? Fluids will always sort themselves perfectly by density in every medium. But even a very non-dense solid like styrofoam could hold something that's 5 kilos, right?
Yes.
To hold it off the earth, even though the 5 kilos would be so much more dense, right? But fluids will always sort themselves to density. So gravity doesn't apply consistently through the states.
Explain that again. Fluids will always sort themselves to density, meaning that they take the path of least resistance?
No, I don't think I said that, but they kind of do. Do you know what a density tower is?
A density tower?
Yeah, it's a science experiment from elementary school. You might remember it once you see it. Let me throw it up real quick.
All right, I want to move back inside the house.
Cool.
It's getting cold out here.
I'm jealous.
Oh yeah, you're in the what you call it?
Yeah.
Oh yeah.
The jungle.
Yeah. You're in the jungle. You're in the jungle, baby.
Yep.
Welcome to the jungle. Come on.
Yeah, that's what's going in my head too.
We got fun and games.
So this is familiar to you, right? At least the concept, even if you didn't build one. I remember building one, I think in second or third grade.
Right.
If we put a cap on this and we shook it all up and then we sat it there, it would go back to looking that pretty in time.
Right.
And the lamp oil would defy gravity because gravity doesn't work on lamp oil, and the lamp oil would begin to rise until it hits a fluid that it's more dense than, which would be the air. That's the only fluid in this experiment that's more dense than the oil. And the solids, like, same thing, they're going to sort themselves inside this levels of density. So gravity is super finicky on when it's going to affect somebody and when it's not.
So gravity is?
Yeah, it's super temperamental. Like, here's one thing that always bothers me. If I put a straw in my drink or my bottle, right, and I sucked, the water would go out and go into me. And just because of this low pressure system that I built in my lungs, the water would then defy gravity and go into my body. But the pure vacuum of space can't rip the atmosphere off of Earth because of gravity, but the low pressure system of my lungs can beat gravity, but the vacuum of space can't. That one I just can't accept.
Well, I think the reason why the atmosphere stays to the Earth is because of the rotation, because of the Earth rotating on an axis.
Whoa.
Yeah.
When a body rotates, it creates a centrifugal force that causes everything on it to be expelled.
Right, but if you add gravity to it, then that would hold the atmosphere in place, right? And then you also said that
this is what happens when you spin an object. Everything on of it leaves. Centrifugal force drags it away. We're supposed to not feel the centrifugal force because gravity counteracts it.
Right, and also space is a vacuum.
Right. So vacuums are stronger than low pressure systems, right?
Right, but then you wouldn't have anything spinning away from the Earth if it's a vacuum, right?
No, you would have the vacuum trying to rip everything off the Earth to fill its absence, because all gases all fluids fill their container. All fluids fill their container. If I put water in a vacuum chamber in the middle of a refrigerator, and that water would start to boil because as a liquid, it couldn't fill the container. And the water would boil until there's above 1 psi, and then it would stop boiling because enough fluid had filled that container. So the vacuum, by every bit of empirical evidence that we have, demands its abscess to be filled. And it is one of the strongest forces known to man. And if you know any scuba divers, they can tell you how dangerous it is if there's a pipe this big that can kill a man if there's a pressure differential on the other side. Because he'll get stuck on that pipe and he'll never be able to move. And if it doesn't rip his body to shreds or literally disembowel him, it'll keep him there until he drowns. One of the biggest things that scuba divers fear is pressure differentials. It is the most terrifying thing in their existence.
So you don't believe space is a vacuum?
I don't believe space is real.
Okay. So where is everything that we see up in the firmament? What is that?
I think it's the heavens, bro. I think God's above us.
Okay, but that's
philosophy.
Yeah. Okay, so
I don't think the fixed stars are inside the dome. I think the sun and the moon are. I'm not very confident on that though. But I think that the glass, for lack of a better word, looking dome above the Earth, I think the stars would be on a thing above that. I think they're outside of our realm.
But what are they suspended in?
The Bible says they're on the firmament. It's a medium that we don't know.
Okay.
Yeah, it's I think that if we go to that philosophical, which I do enjoy that conversation, it's just it needs to be a clear line between my scientific study and my philosophical musings. You know what I mean? I don't have a thesis to state on my cosmology. I have a lot of ideas.
A lot of flat. The people that I've spoken to about flat Earth, they do. It's a lot of theology. You know, there's not a lot of science they can come up with, not like you have tonight.
Yeah, I understand that, and especially because we're brothers, looking at it from a biblical point of view is fascinating, and I love it. I really do. But it shouldn't be confused with geodesy. It shouldn't be confused with the scientific study of the shape of the Earth. They should be different. They're both cool. I love the theology and I love the biblical analysis. I really, really do. And I teach language and I study Vietnamese, so I absolutely adore languages. So I love going into the Hebrew and the Greek words in the Bible and trying to understand their conceptualization of cosmology. I absolutely am fascinated by it. But it's not what made me a flat earther. The Bible didn't convince me. The Bible made sense once I was, but I was perfectly content to believe in the Bible when I believed in the globe.
You believe in what? The Bible.
I said I was perfectly content to believe in the Bible while I believed in the globe. So for me to come and say the Bible proves that the earth is flat is hypocritical beyond all reason.
Right. Okay. Well, let's go on. What else you got? What's the next
So
bullet?
I just say that Dr. Ellis and I are totally in opposite. I will not accept philosophical grounds for the shape of the earth and for the nature of our universe. And then I want to talk about Einstein, because he's the bane of my existence. Because relativities, the two of them together, basically predict that any experiment in the world is going to show the opposite of its hypothesis. So if I hypothesize that the earth is in motion and I want to do an experiment to prove that the earth rotates, well, guess what? The inertial plane is the same as your experiment, so you can't prove that it rotates. And if I want to prove that the stars are leaving us, well, guess what? You can't. They look perfectly centrifugal to us because they're so far away that it's all just relative as you go through. So everything that you try to design, every experiment that you would design to prove that we're the center of the universe or to prove that the earth rotates, relativity says you should get the opposite. If Einstein's right, we shouldn't be able to detect the motion of the earth because the inertial plane should be consistent. Now, there's a problem in the globe model where some people say you can't detect the motion of the earth, and then some people are like, no, you can't. And those are the people who understand Einstein and those who don't. And then the people who understand Einstein a little bit and they're not really sure if you should be able to detect the motion of the earth. And so those are my favorite arguments to start between two globe earthers. So Einstein's way more honest about it than the people who propagate his theories now. Einstein, I don't feel like he was, I don't think he wrote intellectually dishonestly. I don't think he wrote in bad faith. I just disagree with him over and over and over and over again. Einstein was honest that he stood on assumptions, massive assumptions. So I want to make a quick quote by Dr. Mikio Kaku. There's a picture of him. I'm not sure if you've seen him before, but he's one of the most famous physicists out there. He's one of the creators of the string theory, which I'm going to be honest, I really don't know much about string theory. But he's a theoretical physicist, one of the most renowned. He says, in science, we say you make observations and you have a theory, and it's a very tedious process. Wrong. No one I know of in my field uses the so-called scientific method. This is I've got the link to the full interview. It's a 3-hour interview. Barry, he's basically just trying to sell his book. But he seems like a really friendly guy, and so he makes statements like that his students are ready to hear, but the rest of the world's like, whoa. But his students understand why they don't. They know the assumptions. They know the theory of relativity. And they know they can't prove it. That's a Greek quote that's not so important. And this is important because this is from Principia, which is our very first understanding of Newtonian gravity. This is Newton wrote this himself. For the reason of these properties of gravity, I could never hitherto deduce from phenomena, and am unwilling to frame hypotheses about them. For whatever is not deduced from phenomena ought to be called a hypothesis, and no sort of hypothesis are allowable in experimental philosophy, wherein propositions are deduced from phenomena, and not made general by deduction. Everything about Einstein's thinking is deduction. He assumed certain parts had to be true and deducted the rest. I love Newton, ironically. He's one of the best writers, I think, in history. And he has such a clear and concise way to put his words on paper that it blows me away. He's probably a psyop. He has to be. He's too perfect. And then here are like my last reaches as I was, because the beginning of my exploration in this was setting up my structure of thinking. How do I decide what sources I'm going to accept? What you were talking about to me yesterday, like this was the very beginning of my research where I had to go in and go, can I trust Einstein? Can I trust Newton? Can I trust Aristotle? Can I trust Pythagoras? Can I trust Ptolemy? And what did they say, what did they believe, and what am I being taught that they believed? And I found out that most of the time I could trust the men because they understood a clear way of thinking. And the more I read them, the more they explained their way of thinking to me, but that way of thinking is completely lost now. So my mind was open, right? Like I'm ready for this research. I understand what is philosophy, and I understand what is experimental. And that was this whole point of this quote from Newton is, what is not deduced from phenomena ought to be called a hypothesis, and no sort of hypothesis are allowable in experimental philosophy, which is where we're encroaching. Science is an experimental philosophy, wherein propositions are deduced from phenomena and not made general by deduction. So that's the a priori versus the a posteriori. I can use deductive logic as long as my only truth is the phenomenon. And Einstein didn't act like that. He had a truth that it was a heliocentric universe, and never once did he consider the alternative. Never once. So star predictions, eclipse predictions, the moon landing, the ISS, we've got pictures of the world, there are satellites, and what about the Foucault pendulum? These are all these proofs that we have. So I just started picking them apart one by one. It was a huge thing for me when I started to study the computer programs that give you the sky maps. And I found out that they were all using the same technology that a mechanical computer used, called the astrolabe, from 2,500 years ago. It was either made by the Chinese or the Muslims. I've got a picture of it here. And this thing is able to predict where the stars are if you know where you are and you know what time it is, or if you know where the stars are and you know where you are, it will tell you what time it is. Or if you know where the stars are and you know what time it is, it'll tell you where you are. Really cool device, especially when you consider it's like almost 3,000 years old.
So that's that device proves that the stars never change.
Yes, it does.
Yeah.
Or haven't changed in 3,000 years, because they still did. It does. It definitely does. There is, if you go to Wikipedia, they're going to tell you that 10,000 years ago, Polaris was not the North Star. They're going to tell you, I can't remember the name of the star, Thoma or something, TH something. It was the North Star 10,000 years ago. And they're going to quote a couple articles that quote a couple books that quote a couple things, and then you realize like this whole theory was assumed, because if it is a heliocentric universe, then it must have been a different star before. And so once someone wrote that, they all used that as their source to say it was a different star before. There's no ancients who ever recognized anything but Polaris as our North Star. It seems to have never moved in human history, from my independent research. So all these algorithms of these computers assume a geocentric universe, and they use what's called a celestial sphere. Now, they didn't have a concept of a globe Earth, and the computer programs actually don't even compute the whole Earth, but they did have a concept that the stars were a globe around the Earth. It seemed to be the way that they could make predictions. And this is largely to do based on the fact that a human being's point of view is always a dome. And so when you imply the dome is reversed under what we see, the shape is a sphere. So since it's a computer program to predict perspective, if I go into a video game and I need to program in the reflection of a moving object, I will take all that light and compile it as a sphere as well, even though my room is flat, but I need to compile it as a sphere so that the perspective is consistent, because our very perspective as human beings is always a dome.
Right.
And so we assume the sphere. But it still very much is geocentric, and that's how all these computer programs work. They put the Earth, they put all the stars in at equal distances. All the stars are at equal distances in the computer program, and then they rotate. And it's the only way that they can predict where the stars will be. Once they go into heliocentrics, they can kind of get the planets. They can get the planets pretty good, but not great. So we don't really know the exact origins of the astrolabe. Like I said, I think it came from Muslim or Chinese scientists, but the Greeks definitely got a hold of it early on. So these guys, these curves are the fixed stars. And then you rotate that in a circle around. And then these lines represent the Earth. So the backplate is the Earth. And based on where they line up, you're flipping your perspective. So you should be able to see where you are up to the North Pole. The computer didn't work in the Southern Hemisphere. on either model, because the stars just aren't the same ones anymore, and the model's too gone. So I think you can go like into 10 degrees into the southern, but like this line right here would be the very farthest you could get from the North Pole. So I don't. Oh, go ahead.
So what this thing was saying is the Earth is a disk. That way, because there is no southern and northern hemispheres on a disk, right?
I don't think that's a really great argument, even though it helps my point of view, because the makers of this device were not concerned with geodesy. They were concerned with making a clock and a calendar. So all they cared about was the mathematical predictions of the movements of the stars. They were trying to make a tool, not a model. So yes, this does show the Earth as a disk, and yes, that supports my theory, but that's like me pulling a map from 1960s out and going, see, the map is flat. Everyone knew back then it was flat. But, you know, the map's flat because it's a tool and we need to roll it up. Making a ball doesn't make sense even if it was a globe. So I don't think that's the most genuine of arguments. I think this was made to be a clock and a calendar, and my bigger point is the fact that it assumes geocentrism, and the stars have never changed because they still work. And you can make one with a 3D printer, or actually you can make one with paper.
Right, right.
Also, since I'm a language teacher, it's an interesting tidbit that the very first book ever written in English was written by Geoffrey Chaucer, describing to his 11-year-old son how to build one of these. Before then, English was never written because it was the pauper's language, it was only spoken. But Geoffrey Chaucer's son's Latin wasn't good enough to read, and he wanted an astrolabe. Chaucer wouldn't let him use his. So he's like, if you want one, you need to build one. So thus the first English book was penned.
That's cool.
So I ran into eclipses, and I found out that no human being on the planet can predict a single eclipse based on the flat Earth or based on the heliocentric model. And I've got so many problems with this, because that should be an easy one. If Kepler's math should be able to predict the motion of the planets, and eclipses are caused by the moon, then we should be able to predict them. All eclipse predictions are done, like I said, based on that cycle, that 18 years, 11 days, and 8 hours. It's called a Saros cycle. and I'm going to show this to you because this statement is so wild that it needs to be verified. Every single prediction of the U.S. government in its entirety are done by this guy here on the right, Fred Espenak, and he assumes full responsibility for their validity. No one in the government has ever assumed full responsibility of anything, ever. Fred Espenak published a book that had 5,000 years of eclipses, and they're all based on observations. He's not that much of a mathematician or a cosmologist. He's more of an anthropologist. And so his great work in predicting eclipses was traveling to every part of the world, looking for their ancient writings and their teachings and their recording of all their eclipses, and then applying them to our modern calendar. All right, so here it is. This is right from nasa.gov. I took this screenshot. All eclipse calculations are by Fred Espenak, and he assumes full responsibility for their accuracy. Have you ever seen a .gov website that assumed full responsibility for anything, let alone accuracy? Like, that's red flags. And it hasn't been updated, and it's perfect. And every single computer program just downloads a database from this book and then will force the eclipses to happen when they need to. Their model doesn't have the bodies in the right position for eclipses to ever happen. The moon and the sun and the earth are never lined up quite right. They're usually pretty close, but they're never quite perfect. So it has to override the eclipses because eclipses just don't work on the heliocentric model. So I want to talk about one specific example, and I'll give a really great proof of why what I said is so true, that eclipses just don't work on the heliocentric model. We're going to look at the Great American Eclipse on August 21st of 2017. This eclipse began over Washington, pretty much out in the ocean by Washington at like 3:46 UTC, and then it moved eastward across. The Harvard article that I sent that studied the bend of the stars through the solar corona was based on this eclipse, and they were in Wyoming. The sun's shadow ended down by Cuba in the Atlantic Ocean, and the eclipse ended at 9 with the very ending of the eclipse. So let's visualize what we just talked about. That's how the eclipse went, right? We're going to rewind. And that's how it went. And you top right, you can see the time. 6:30, 7, 8, and then 9, and it's gone. All right, so now let's take one that's recommended by NASA pretty much. This is called Solar Scope. You can see it at solarsystemscope.com. You can use any of them. They're pretty much all identical, but this one works really well and is free, so I use it a lot. So I don't know how good or how well you can see, because I want to specifically talk about the U.S. on this Earth.
I can see it. You
can see the U.S. All right, good. So this is the time, 10:45. Now the Solar Scope website was having a problem when I took these screenshots. So I'm in Vietnam time, which this is right when the eclipse started. And you're going to see I'm going to go forward. Oh, I'm going to try to go forward. There it is. All right. So do you see the Earth spinning?
Yeah.
You see the direction that the United States is coming around?
Yep.
So now I want you to envision that the sun is the light source, and here's the start of the eclipse. I want you to envision where the shadow would land.
Well, the Earth is rotating differently. It's not.
The Earth is rotating differently. What?
Well, yeah, because this sphere right here in the middle is
the moon.
This one right here, that's the moon, right?
No, there. That's America.
No. Hang on.
Okay, I think you're talking about the moon then. You just missed it because you're on a little phone.
No, I'm not on a phone. I'm on an iPad.
Oh, I see. This guy, right? Yeah.
Right here. This guy right here. I'm pointing at him right now.
Yep.
See him right there?
Yep.
Okay.
That's the moon.
So that's the moon, right? That little green dot. So the Earth is rotating, from my perspective, it's rotating from left to right.
Correct.
So the eclipse should have started somewhere down here in the Caribbean and ended up in Seattle.
Correct. That's correct.
So why do they say it went the other way?
It did go the other way. It absolutely did. And it was observable by every American. And we know that it went the other way. We know for a fact that the shadow went the other way because we all observed it.
So why are they showing it backwards?
Because eclipses don't work on the heliocentric model.
Which is the model that we rotate around the sun.
Right. This is a heliocentric solar scope. And I'm showing you that it doesn't work. I'm using their technology and showing you the position of the planets is wrong for the eclipse that we observe.
So what you're saying is because the sun rotates around us, or not rotates around us, but is inside our dome, our firmament, that's why it made sense, because the sun went according to...
I haven't really analyzed the eclipse on the flat Earth model, to be honest.
Well, put the flat Earth back up for a second.
Sure. Because I don't think in the flat Earth model, I don't think that the an eclipse would be caused by
The moon.
No, yeah, I don't think the eclipse would be caused by the moon.
Well, then what caused it?
I have no idea what causes it. All other, like if I go back to the ancients, because that's the only one that I can draw from. They think it's another body that like comes in front of the old ones,
within
like the
firmament?
Chinese. It would have to be because it'd have to be in front of us, right?
So where does that body go when it's not?
The idea is that it's always here, but it's not visible to us. It was what the Greeks and the Chinese both independently came to. I don't know if I buy that, but that is what the Chinese and the Greeks, they even had a name for it, and they said the same thing with the lunar eclipse, that something would come and devour it and stain it red, kind of like a transparent glass went over the moon for a second. Is how they described it. And the bodies are always there, but we can't tell except during the phenomena where they're lined up with the moon and the sun. So there are a lot of astronomers that went looking for them in non-eclipse parts of times.
So what you just showed me, that model from NASA, that the Earth was rotating in the opposite direction, okay, proves that
there's something wrong. That's it.
It
doesn't prove that the Earth is flat. It just proves there's something wrong.
Okay, but this also proves that there's something wrong with this model too. Wouldn't you say? Well, because you're saying that there's something within the firmament we can't see, but you said that the sun is within the. Did you say that the sun and the moon are inside the firmament?
I think so.
Okay, so this object that we can't see, if it's not the moon, then wouldn't we be able to see it at other times?
That I kind of have that same question too. So I would think that we should be able to find it, even if it's not like super visible to us. There should be other phenomena that points to these bodies. I totally agree with you, and it's one of the reasons I said that I'm not sold on this theory. And there are a lot of ancient astronomers who went looking for these bodies, not during eclipse. But I have not found any convincing stories of people finding them. There are a few who say that they have. I'm just not convinced.
Also, the sun in your model here, the flat Earth, is going clockwise. So there again, the eclipse would have been backwards in the way everybody observed it, right?
No, because the sun, if the object, whatever did obstruct the sun, because we know something obstructed the sun. We all saw it blacken, right?
Right.
So the idea would be if the object was going like this, then the shadow could still happen at the same time, because that would just be a thing of perspective, and I would need to get a flashlight and two bodies to figure out how to make that perspective work. But it would be depending on where the obstruction is coming from for us to know the direction of the shadow.
I see.
So actually, that would be something, now that you brought it up, that's something that I want to do. I want to put a map on my table and get a flashlight, because then maybe I can start to look for whatever this obstruction was. One interesting thing, just because we are Christians, one interesting thing is 3 times in the Bible, it's referenced that a solar and lunar eclipse will happen simultaneously. To my research, that's never been recorded in history, and obviously totally impossible in a flat Earth, in a globe Earth model. And it's like pretty dark days. Like one of the times is when Jesus dies, one of the times is when Jesus comes back, and I can't remember the other time. It's like pretty serious stuff going down when a sackcloth will be thrown over the sun, and the moon will glow red, right? A red moon is a lunar eclipse, a full lunar eclipse. And when do we see something like a black sackcloth go over the sun? A solar eclipse. So these happen. So that's an interesting thing, because once we're talking about what actually causes the eclipse as opposed to the phenomena, we are in the world of cosmology and philosophy. So the Bible plays a role in my thinking of cosmology. It very much does. Sure. Not the flat Earth, but my understanding of cosmology. If I could get in a spaceship and go observe space, then it would no longer be a philosophical study to me. It would then be a scientific one.
Right. But saying that you go on a spaceship would mean that you would have to believe that there is actually a space, right?
Yeah. Like I would be terrified.
But
You're just trying to kill me, aren't you?
No. I didn't mean to say that to try to kill
No. I'm making a joke because that's what all the globe earthers say. Like, why don't you just go up in a spaceship? It's like you really don't understand me, do you?
Well, I understand that if you don't believe there's space, the whole concept of going into space would be horrible. Really,
Right. Am I gonna hit the firmament, or am I just gonna end up in the ocean?
Right. What is a selenial?
Selenium is the way to learn how to pronounce it, because those are the two Greek words. Selen means moon, and helion means sun. So a selihelion eclipse is things that are observable, and I even have a couple videos we can take a look at. And it's when there's a lunar eclipse going on, but the sun is visible. So you can see the sun during a lunar eclipse. So let's think about how a lunar eclipse should work. Let me give my annotate.
The lunar eclipse is when the Earth gets between supposedly, right? The Earth, the circular Earth, the globe Earth gets between the sun and the moon.
Right.
Right?
Hey, these tools make it cool.
Sounds just like your pop. These tools, man, make it cool.
That's not great. Like that, right?
Right. So how can you see the sun and the moon at the same time, though?
Oh, you shouldn't be able to. Like it should be. Oh, you mean ever or during the eclipse? Yeah, during the eclipse you shouldn't be able to. It should be totally impossible. Because the people here in theory should be able to maybe see both the moon and the sun at the same time, but they shouldn't be able to observe the eclipse because from their perspective it wouldn't be eclipse.
Right, because they're on top of the Earth.
Exactly. So
top of the
let's take a look at these videos.
So you're saying that it's possible if the Earth is a disk.
It definitely is, because I don't think that the sun is super involved with the lunar eclipse. I don't think the sun is
heavenly mass.
What's that?
It's this other heavenly mass or heavenly body.
That's the general consensus for not just like 2020 flat Earth community. That's the general consensus from ancient Chinese flat earthers and ancient Greek flat earthers, right? So it's not a theory that I'm just going to dismiss super easily, but I'm not convinced at all.
Right.
Definitely not convinced of it. Like maybe it's I don't know. I don't think like the light can go out of the sun because like there's still light other places when the eclipse happens. So it has to be an obstruction.
So you reiterating here just to make sure I understand you correctly, you believe the sun and the moon are within the firmament?
I do.
Okay.
I would say most that one, like the community's not decided on at all. There are ideas that it might be a reflection on the firmament, and then there are obviously ideas that it might be above. So there you see the blood moon.
Right.
Full on lunar eclipse. And look at that sun. He's going to go find it. It's in the trees.
Right there. I see it. All right. The blood moon means that the Earth is between the sun.
Lunar eclipse. The red moon is a full lunar eclipse. That's the phenomenon. The theory you're right. The theory in the mainstream science heliocentric model is that the Earth is in between the sun and the moon.
But in that picture, you can see both of them.
Correct.
So what is between the sun and the moon? Can you look up? You see what I mean? Is there a picture of something above that picture you just showed me? You know what I mean?
Like if the photographer took his camera straight up.
Yeah, you should be able to see the object that's causing the eclipse, right?
Oh, no. So my understanding of the object is not that the object would be between the moon and the sun. The object would be between the moon and the viewer. That's my understanding of
it. The viewer and the sun?
No.
The moon.
The moon and the viewer. So I'm looking at the moon, and then all of a sudden this comes in front of it, and I'm like, oh my gosh, the moon has turned blue. Can you tell? Oh yeah, it's a blue transparent model. Right? So my eye gets eclipsed by this from my camera's point of view. If it gets eclipsed from the light's point of view, the color of my face doesn't change. This is in between me and the light. I guess it does a little bit, but not dramatically. But when it goes between the viewer and me, everything changes.
Right.
So that's my understanding of how the Chinese and the Greeks. And the Chinese wrote of it like a monster that ate the moon at times and ate the sun at times. But the whole world doesn't go dark. So that's why it seems to me that the eclipses in both points of view needs to be an obstruction between the viewer and the body.
Right. Well, that makes sense. But Okay, all right. I just answered my own question. Go ahead. What is this picture of?
Same photographer. Now he's in Joshua Tree National Park, and this is an eclipse a couple years earlier. He is an eclipse hunter. It's all he likes to do, and this is another selenohelian eclipse. So you'll see the sun rise, and then he'll turn around to show you the moon mid-eclipse.
But a blood moon, you're saying a blood moon is an eclipse?
It is a lunar eclipse, yeah. The blood moon is just the older term. Before the heliocentric model, we call it blood moon because it goes red. This one is the end of the eclipse, so it's not. Actually, it's still kind of red.
Yeah, but why? What I don't understand is the moon looks like it. Okay, from what I understand, the moon is red because it's cutting through more atmosphere as it's coming up over the horizon.
That is the official explanation, I think.
Okay, but a lunar eclipse would be like the total blackout of the moon, right?
No, when the moon totally blacks out in a lunar eclipse, the shadow switches from black to red. It's quite an amazing. It really is quite an amazing sight.
Okay, so
only in the purity, like even looking at their explanation, it doesn't make sense. It's so silly. So they're telling you that you can only observe it from here, right? Because that's where the shadow is. You've got to be inside this arc to be able to see it.
Right here.
Yeah, and we just saw homeboy with that sun right up there. And he has been hunting those, but he hunts all eclipses. I found him by happen chance
it has to be right in there. You have to be right in there in order to see the red.
Yep. And you can
But this guy was taking photographs of it when you can see both bodies.
Yep.
Huh. Interesting. So that confirms the theory that the Earth and the Sun are in the firmament.
To me, it confirms it continues on my previous point that eclipses don't work in the heliocentric model.
Heliocentric, which is their model.
Yeah, that is an affirmative statement I'm making, and now I am not telling you I have eclipses figured out on my model because I don't. But this was when I was trying to use eclipses to prove heliocentrism when I began the study. And lo and behold, everything fell in my face. And I was like, actually, we don't know anything about eclipses, and they make no sense, and they don't work on our model, and nobody talks about it, and just shut up and look at the pretty moon.
Well, in this picture here, okay,
Mm-hmm.
in this picture here, if this was actually true, you wouldn't be able to see the moon at all, much less it being red, right?
I also think that, but the mainstream explanation is that the gravity of the Earth bends the light of the sun around and then warps it to a red shift and then shoots it to
Well, it sounds to me like it takes a hell of a lot more faith to believe that than creation.
Yeah, you're preaching to the choir, man. You're preaching to the choir on that one.
Hey, can we finish this tomorrow night?
Do a part two? Absolutely, man.
Can we? Because I got to go to work tomorrow, and
yeah, no worries.
What time is it?
It's 11:43 for me, so it's not midnight for you yet.
10:43 here.
All right. Oh, you're an hour behind. Cool.
Yeah.
Totally.
Incredible research, Joshua. I like it.
Thank you.
I really do. And you know what's funny? I'll tell you this before I go, that all day today, I wasn't even thinking about, I knew we had this, set up to do tonight, but I wasn't really thinking about, being open. And I mean, I knew that I was going to come into it with an open mind, but so many things were like, keep an open mind. The only way, you grow and you flourish and and you mature is open-mindedness, open mind. Just that theme was all day today. Kind of interesting, wasn't it?
Yeah.
And then when I sat down to talk to you, it all came back, and I was like, yeah, this is a good deal. So anyway, I appreciate you taking all this time, though.
No problem, man. I appreciate you sitting there and listening to me and challenging me, and I mean, it needs to be.
I don't mean to sound challenging. I just have questions. That's all. I mean,
well, I see challenges as in a peer review type of way. Like that's good. A scientist needs to be challenged when they state their thesis. Like I need. That's how you get your doctorate, right? You defend the challenges to your thesis.
Right.
So that's.
Are you gonna? Yeah. Are you going to continue in the scientific vein, and you're going to go for a PhD in science?
I doubt any academic industry will give it to me, but I will try to publish a thesis. Yeah, I'm not ready yet, but that's what this presentation is, the first formulation of my thesis. So I will eventually turn it into a thesis statement and a paper and publish it.
You may get an honorary degree or something.
Possibly, or I may be laughed out of every academic hall for the rest of my life.
Well, that is the mainstream. Now, just let me ask you just one question before I let you go, and that is, what is the purpose of them lying to us about the Earth being flat? Besides what you said last night, that it keeps us from being in connection with the true Creator.
So once again, then we're into some theology and philosophy, but in my logic and my thinking is that this 500 plus year lie, this elaboration, is far too in depth and far too organized for man to be at the root of it. There must be an evil principality that's leading this, in my opinion, because it's beyond man's ability. I feel. It really is. Mm-hmm. This kind of magic and this kind of mind control has got the whole world thinking this. If I'm right, I believe it's beyond the capability of men. So I don't think the men have a motive so clear, except it makes people easier to control. Atheists are easy to control. Materialists are easy to control. Every government's fine with that. If you explain to the government, no, go along, your population won't rise up, there won't be revolts, they won't get too religious, everybody will be fine, they'll work, they'll pay their taxes, and they'll die, just like you want them to do. They'll fight for their nation because they believe in it. And even Ronald Reagan started talking about how Ronald Reagan, during his presidency in front of the UN, talked about how the only thing that could truly unify the world would be an alien invasion. Ronald Reagan said this in a speech to the UN while he was president. And that kind of thing, to recreate the Tower of Babel, where all man stands together to rise up to defy God unified, that kind of thing takes a lie like this. So It's about spiritual warfare. It's very core. Everything about this is.
That's cool. That's cool. Yeah. I kind of sort of feel like that is a more, that's a pretty legit answer. You know what I mean? Makes sense. It makes sense. But anyway, tomorrow, 7:00?
Yeah, do it same time.
I'll send you a telegraph thing if I don't make it back from work before then.
Okay, sounds good, man.
Because I sometimes work till 9 or 10.
Oh, do you really? Oh, wow.
Yeah,
Gotcha.
it's kind of crazy, but
all right, cool.
All right, God bless you. Good night.
All right, you too. Love you, brother. Take care.
I love you too, man. See ya.
Bye.